Welcome to this Concept Explainer, brought to you by CBSE ScoreLab of ProfSam.com, that is ProfSam.com. Today we are taking a deep dive into the introduction of Unit 9, Ray Optics and Optical Instruments. Our goal is to make sure you understand the core concepts really clearly for, maximum exam safety and application.
Right. Ray optics can be a bit tricky. I think it's because it feels like it's half geometry and half physics, and sometimes it's hard to see where one ends and the other begins.
Absolutely, it can feel that way, but you've hit on the key word there, geometry. That's exactly what we're going to lean on. Okay, so let's unpack this with a very simple observation. Before we get into any formulas, just tell me this. When you look into a shiny spoon, the side that curves in like a little cave, what happens to your face?
If I hold it really close, my face looks huge, and it's upright. It's almost like a weird magnifying glass.
Okay, what if you move it away?
If I move it far away, then it flips. Suddenly my face is tiny and upside down.
Exactly. That is the magic we're talking about. That sudden, dramatic change, upright and magnified, then suddenly flipping to inverted and small. That's all happening because of how light bounces.
And it's not just bouncing, right? I've always wondered about, say, a swimming pool. The bottom always looks closer than it actually is.
Yes.
It feels like an illusion.
It is an illusion. The spoon is all about light bouncing, which we call reflection. The pool, on the other hand, is about light bending as it comes out of the water. That's refraction. So the big question is, why does light choose to bend and, cheat our eyes? This bouncing and bending, this is the entire foundation of ray optics.
Okay, so what's the core idea then? How do we even start to model this?
So the core idea is actually a very clever simplification. We know light is an electromagnetic wave, which is complex. But for most big-scale things, we can just pretend it travels in a perfectly straight line. We call this imaginary line a ray. So ray optics is just a geometric approximation of reality.
But why is that allowed? Aren't we ignoring really important physics like diffraction and interference?
That is a brilliant question, and the answer is scale. We can get away with this lie because the wavelength of light is tiny, measured in nanometers. It's minuscule compared to the size of the objects we're using, like mirrors or lenses.
So as long as the mirror is much, much bigger than the wavelength, the straight line model works.
Precisely. And this simplification gives us immense predictive power. Without it, we couldn't design a camera lens or a telescope or even the glasses you might be wearing. We use simple geometry to calculate exactly where an image will form. It's incredibly useful. Think of it like this. Here's an analogy. Imagine light rays are like cars on a busy highway.
Okay.
On a smooth, uniform road, the cars travel in straight lines at a constant speed.
Right.
Now, what happens if a car hits a different surface? Like it suddenly drives into a patch of soft mud.
Well, it would either bounce off if there was a barrier, or it would slow down and probably change direction. Sort of skid.
Exactly. That's it. Bouncing off is reflection. Changing speed and direction when entering the mud. That's refraction. The model just asks, where will this car end up?
I see. So we're just tracking the path.
Yes. Now, to build a strong mental image, picture this. A dark room, and you have a thin beam from a laser pointer hitting a flat mirror. The beam coming in, the incident ray, is perfectly straight. It hits the mirror, and instantly it bounces away as the reflected ray. What's the most obvious thing you notice about that bounce?
It's symmetric. It's not random at all. It seems to bounce off at the exact same angle it came in with.
That's the heart of it. The angle it makes with the normal, that's just an imaginary line perpendicular to the surface, is exactly equal for the incoming ray and the outgoing ray. That predictable geometry is rule number one. Now let us see how insert defines these fundamental laws. Let's start with reflection. Could you please read the official definition for us?
Of course. It says the angle of reflection equals the angle of incidence. And the incident ray, reflected ray, and the normal to the reflecting surface at the point of incidence lie in the same plane.
Very good. That's the perfect exam-safe definition. And what's amazing is that this simple rule, angle I equals angle R, is valid at every single point on any reflecting surface, whether it's a flat plane or curved like that spoon.
But wait, if the rule is so simple, how does a curved mirror create such a complicated image?
That is the secret. Because the surface is curved, the normal, that perpendicular line we measure from, is pointing in a different direction at every single point. So when parallel rays of light come in and hit the curved surface, each one obeys the I equals R rule, but with respect to its own local normal. This symptomatically directs all the rays to either meet at a point
Or spread out.
Exactly. A concave mirror brings them together, a convex one spreads them out. The curvature organizes the bounce.
Okay, that makes sense now. The law is simple, but the geometry isn't.
Precisely. Now let's look at refraction, the bending of light. This happens because light actually changes speed when it enters a new medium. Could you please read the mathematical definition, Snell's law?
Yes. It says, the ratio of the sine of the angle of incidence to the sine of angle of refraction is constant. We have sin I by sin r equals n21, where n21 is a constant called the refractive index of the second medium with respect to the first medium.
Good. That constant n21 is the hero here. It's really the ratio n2 divided by n1. You can think of n, the refractive index, as a measure of how optically dense a medium is, how much it slows light down.
So a higher n means a slower speed for light.
Exactly. And if a ray enters a denser medium where n2 is greater than n1, it slows down and bends toward the normal. But if it enters a rarer medium where n2 is less than n1, it speeds up and bends away from the normal.
So the cause is the speed change, and the effect is the bending.
You've got it. Hope everything is clear so far. This concept explainer is from ProfSam.com. That is ProfSam.com. Let's quickly run through a calculation to see this in action. Suppose light goes from air, where n1 is 1, into glass, where n2 is about 1.5. And let's say the light hits the glass at an angle of 30 degrees. We just use Snell's law. n1 sine the 1 equals n2 sine theta 2.
Okay, so that would be 1.0 times sine of 30 degrees, which is 0.5.
Right, so on one side we have 0.5, and that equals 1.5 times sine theta 2.
So sine theta 2 is 0.5 divided by 1.5, which is about 0.333.
And if you take the inverse sine of that, you get theta 2 is approximately 19.5 degrees.
Ah, so it went from 30 degrees down to 19.5. It bent toward the normal, just like you said, because it entered the denser medium.
Perfect. This basic understanding, rays, reflection, refraction, this is the alphabet of optics. Once you master this alphabet, you can start building words and sentences, which are spherical mirrors and lenses, and then paragraphs, which are complex instruments like microscopes and telescopes. Now, let's address some silent killers. These are common misconceptions that feel right, but will definitely lose you marks in an exam.
Okay, I definitely need to hear these.
Wrong idea number 1 is about reflection. Many students think the angle is measured from the surface of the mirror. They forget about the normal.
Oh, I can see myself making that mistake. So if a question says the light hits at 30 degrees to the surface?
You absolutely cannot use 30 degrees as your angle of incidence. That's the trap. The angle of incidence is with the normal, so it would be 90 minus 30, which is 60 degrees.
Got it. Always measure from the normal, not the surface.
That's correct. Now, wrong idea number 2 is about refraction. Students often remember one example, like air to glass, and assume light always bends toward the normal.
But it depends on which way the light is going, doesn't it?
Completely. The direction of bending flips if the light goes from glass back into air. So you must remember the rule. Entering a denser medium, light bends in toward the normal. Entering a rarer medium, it bends out, away from the normal.
Denser in, bend in. Rarer out, bend out. Okay, I will remember to check the refractive indices first.
Excellent. Now, to lock these ideas in, let's use a couple of memory anchors. For Snell's law, try to remember this phrase. Snell equals speed changes, so light ends up bending. Law links the indices to signs.
That's actually very helpful. It connects the cause to the formula.
And for reflection, try a physical gesture. Point your finger straight out, that's your incident ray. Imagine a vertical line coming up from where your finger touches the table. That's the normal. Now, pivot your finger symmetrically around that normal. That new direction is your reflected ray. That physical motion embeds the law in your mind.
Okay, I'm trying it now. Incident, normal, reflected, symmetrical. I see it.
Perfect. So let's summarize with 3 essential takeaways from today. First, the ray model is a geometric approximation that works. We treat light as straight lines because its wavelength is just too small to matter for objects like mirrors and lenses.
Right. It's a useful lie.
Second, the fundamental laws are everything. Reflection is simply I equals R measured from the normal. Refraction is Snell's law, and the bending direction depends on whether the medium is denser or rarer.
Got it. I equals R and Snell's law.
And thirdly, something we touched upon, total internal reflection. This happens when light tries to go from a denser to a rarer medium at a very high angle. It gets trapped and reflects perfectly. This isn't just a curiosity. It's the core principle behind fiber optic cables that power the internet.
That's a really important application.
Immensely.
Yeah.
Okay, to get maximum marks in 12th CBSE physics, chemistry, and maths, visit ProfSam.com.
That is ProfSam, right?
Yes. ProfSam.com. Study well and stay curious. Good luck.